Okay, what we want to do here is to continue with objective 1.8, which was configure and then to troubleshoot IPv4 addressing. I have a couple of abbreviations here: CIDR, classless internet domain routing, which means we're not going to use the networks that are specified by the classes, the class A, B, and C that we talked about in the previous lesson. And then VLSM is variable length subnet mask. What that means is that when we do a CIDR, each of the subnetted networks is going to be the same size. In VLSM, they're each going to have a different number of hosts in it. So when we look at this thing, and hopefully it'll make a little more sense when we get through here. So the objectives: why do we want to subnet? The subnet mask function, which we've talked about, tells us how much of the address is network and how much of the address is hosts. The process to subnet, how many of whatever, and we can't create addresses here. We have X number of 8 bits per octet, and that's all we can use. And then we have to use our 2 to the n, and each of the things that we use has to be a power of 2 because that is the only things that are going to be available to us. So the process here, the network address and the broadcast address we've talked about, we can't use them. So when we do subnet, we're going to lose 2 addresses for each subnet that we work. We're going to divide the network, and we're going to divide it into things called increments. And the increments are basically going to be how many total addresses are available in each of our networks, which is going to be a shortcut way to do this. There are a couple of ways in the videos that you'll have on subnetting are going to show how to write it out in binary, as well as how to use the increment. I think that the increment is a shorter way to do this. So, and then VLSM are different size networks. Instead of having a bunch of networks all the same size, VLSM are going to have different ones. But why subnet? The answer here is to relieve congestion. And when we look down here at the bottom, we have a single broadcast domain on these 2 different switches down here, 2 different networks, single broadcast domain, because remember, a router is the device that divides the broadcast domain. So what we have in this case is these machines are in a broadcast domain and these are in a broadcast domain. When we get this, they all get broadcasts for both networks, regardless of whether they should get those addresses or not. Let me try to demonstrate that with a packet tracer simulator. Let me drag this over here, and what I have here are 2 different networks. This one has 2 IP subnets in it, 192.168.1.0 network, and if we go in here and look at one of these things, and we'll show IP config. Okay, it's IP config. Get too many of these things going on. The show would be for Cisco, obviously not for Microsoft, but the IP address, and I didn't put a default gateway in it, but the 192.168.1.3, it's class C 255.255.255.0. So everything that starts with 192.168.1 should be in that network based on what we've talked about for the subnet mask. Covers the first 3 octets. The 255, the last address, the one that would be all ones, would be the broadcast address. This is a 2.3 or the 2.0 network, and if I do an IP config here, 2.3, 255.255, same thing, but anything at 192.168.2 would go there. So what I want to do is I'm going to put it in demo mode so that we can see the packets going back and forth. So if I go into this guy and then I ping 192.168.1.255, it should broadcast should go to everything, because that's what a broadcast does. If I do that, then I've got to close this and go down here and play this as it goes through the event. It's a little slow. Times are in here somewhere. I don't know where it is. But anyhow, we're going out all the ports to all of the different destinations. So I have broadcast traffic. It gets here that says, okay, I'm not on that network. I can't talk to this guy. It doesn't answer it, but the traffic gets there in any case. And if we go back here, the one on its network is actually answering it. And then we can go back and look at this reply from 1.3, and it's finishing it up right now. Now if we go down here to the one with the router stops broadcasts, and do the same thing, then we should be able to see what happens here. So in this one, it didn't have a whole lot up there, but we're going to do the same thing, except I want to go into demo mode. Ping 192.168.1.255. So we'll go in here and play it again. So we go up into the switch. Switch is going to send it out, and then it should stop at the router. The router is going to answer. It stops at the router, so the broadcast does not go across the router. It responds because it's got a 192.168.1.1 address on it. So we get these things. Let's go back into here and go back into actual kind of live mode here, maybe. But anyhow, we're getting replies from 1.3 and 1.1, which are the only two addresses that are in that broadcast domain. So routers create broadcast domain, give us some isolation so that we're not sending all the traffic to everything all of the time. So add some security, relieve congestion, a single broadcast domain. We need to divide the network into smaller broadcasts, and that's what we're doing, the single versus the two broadcasts, the demo of what happens with the traffic. It does add some security because we can't see the broadcast traffic from everything. We can also now filter traffic with access control lists. Determine we're here, and we will write some access control lists. But what an access control list does is it limits which traffic can get from point A to point B, which traffic that we're able to send. So if I go over here onto my router, and in here, let's say that we put in a server of some sort, and then maybe we put another address up here. What I can do on this interface is only allow, maybe this is admin, we'll be able to get there. This may be on the payroll. I always like to use payroll because that's where we would all like to get to change our pay rate. But we have admin, so we would allow admin to get into there, but then our access control list for our students would say no, they can't get in, so they would be denied. Admin and payroll would be allowed, and we can and will learn how to do those sorts of restrictions, so we can filter and we can monitor and control bandwidth. When we get the quality of service, we'll learn how to assign a certain bandwidth or higher amounts of bandwidth to certain machines. So the subnet mask, and we've talked about that a little bit, the subnet mask tells us, and I think that I said these things earlier, function is to specify how much of the address is network. So how much of the address is the network address? Remember, the network address comes first. And how much is host. Anything that's not network, anything that doesn't have a 1 in it, under it in the subnet mask is going to have a 0. So the 255 would be 1, 2, 3, 4, 5, 6, 78.123.4 and all zeros after that. This says that anything, any part, any digit that has a 1 under it in the subnet mask is part of the network. Any part that has a 0 in it is part of the host definition. And we looked at the class full 255.255.255, 255.255.255. So in each of these we're creating more networks and fewer hosts per network. More net, fewer hosts. So consecutive ones and then consecutive zeros. We can't mix the ones and zeros. We can't have a subnet mask that looks like this. That's not valid. It's got to be all ones, and then once we're done with ones, we finish up with zeros. Determines the network and broadcast address. The network address where the host bits in here are all zeros, and I like to use the class E's because the arithmetic is easier. Everything, it all works the same way. But if we had a 192.168.1.0 with a 255.255.255.0 address, the all zeros, this is going to be the network address. The one that is all ones in the host, which in this case would be the 255, just like we pinged earlier, is going to be the broadcast address. So yeah, and in class full networks, the network address is going to be 0 and the broadcast is going to be 255. When we start subnetting, that's not necessarily going to be the case. We have to look at which part of it is all zeros and which part of it, or which address is all zeros and which address is all ones. And those are the ones that are going to specify which is broadcast and which is network address. So the process, the steps in subnetting in an enterprise network, any kind of network, are identify the number of subnets required for the network. We can do subnets or hosts per subnet. So subnets, or hosts. And once we determine one or the other, we now know how many bits are allowed for the other one. The example that I'm going to have says we need 6 subnets. We have to have a power of 2, so we have 2 to the 1, which was 1, right? 2 to the 2, which is 4. 2 cubed is going to be 8. So that's right. So 8's got to be the number that we want. 2 to the n has to be greater than or equal to the number that we need. At one time, and I think if you still do Microsoft, we couldn't use the 0 network and the broadcast network. We can do that in Cisco. They had this really clever command that says subnet 0. So we don't have to worry about subtracting when we do network addresses. So that means that if we had 3 bits and we use 3 bits for network, since we have a total of 8 bits, and we'll presume we're in the last octet, 8 minus 3 would be 5, so 2 to the 5th, 2, 4, 8, 16, 32, 32 addresses, 30 usable, because the all zeros is the network and the ones is the broadcast address in this thing. So we identify the number of hosts that need to be accommodated per subnet, one or the other. You can't create addresses when we do this thing, and they'll work out when you do testing. Select a subnet mask based on the class of the IP network. So if we were subnetting 192.168.3.0 network, our default subnet mask would be 255.255.255.0. And then in this case, we had 32 addresses, and we're going to do this shortcut one right here. 32 addresses, so we always start with 0. So my network addresses, since we have 32 addresses per, we just put them in 0, 32, this is called the increment, sometimes called the magic number. 32, and we add 64, 96, what is it, 128, 132, what is it, 92 is 10, I don't care, 3, 2, 5, 6, 160, 1, 2, 3, 4, 5, 6, 160, 192, and then we add 32 to that, 4, 224, and then if we add 32 to that, we get up to 256, which is the end, obviously, of the network. So our network addresses in this case, with the increment, 5 bits left for the network address will be 0, 32, 64, 96, 128, 192, 168.3, and on and on and on. And then the subnet mask, we could either add up the first three, 192, 224. The little trick is if we take 256 and subtract the increment, in this case 4, 224, it's going to be the subnet mask. So when we subnetted each of these network addresses would be 255.255.224 for the subnet mask. The broadcast address would be one less than the next network address. So the broadcast address for this guy would be 31, and for this guy would be, what is it, 64, 63, and on down the line. The first usable address is the network address plus 1. The last usable address is the network address, or excuse me, the broadcast address minus 1. And this is an organization has a network address of 192.173.28. They would like to set up 6 subnets to segregate traffic across 6 departments. To do this, the 3 higher order octet bits, the higher order are the ones on the left, so we have the high order here. What we're really doing is we're moving the subnet mask to the right. So the high order bits we're going to take, instead of making them hosts, which they were, we're going to convert them to network bits. So we do this. To do this, the 3 high order bits and the last octet can be reserved for subnetting. 255, 255, 254, 6 subnets capable of supporting 3 hosts each. It should be 224. 254 wouldn't do that. It should be a 224 in here, just like we did up here. So we have 6 subnets, each capable of supporting 30 hosts, because we can't use the network address and we can't use the broadcast address for host addresses when we do this operation. So in this, the example, which basically I think I've already done, but I'll step through it here quickly. We wanted 8 networks. To do 8 networks, we've got to go to the value bits and how many, which is, I think, a useful little table here. But how many, we go to 8. 8 was the lowest number that we could get to be inclusive of 6. So we have to use 8. So basically we're winding up with 2 subnets that we're not using, but we're wasting addresses, but we're creating our broadcast domains, and we have done some isolation, and we're able to now do filtering and those sorts of things. 5 bits for the host, 2 to the 5th, 32. 32 is equal to the total. So the hosts, or the usable, is 32 minus 2. Can't use the network or the broadcast, which leaves us 30 total addresses. Can't use the network and can't use the broadcast address. 32 is called the increment, or the magic number, sometimes the magic number. And magic because the total number of hosts per subnet is those, and this is the 0, 32, 64. We just start out with the increment. That's how many total addresses are going to be in each of our subnets. So those are also going to be our network addresses. And then the addresses start with 0 and increment by 32, just like I did in my scratched on example. Continue the subnet mask. We increase the mask by moving the ones to the right. Move the ones to the right, so we have our dot whatever 1 1 3 of them, and then 1 2 3 4 5. Draw a line, network, and host. And this is this example over here, the new mask properly written here, 224. Also, the mask is 256 minus the increment, which we did earlier. 256 and the increment is 32, which is also going to give us the 224. The iteration over here, as we go across this thing, 0 0 0, we add the ones, and then we have the possibilities are 0 0 0 0 0 1 0 1 1. You can add the binary up and you'll get the numbers that we got in the previous one, the 0 32 64 96 and on down the line are the numbers that we would get, the network addresses that we would get if we did it using the binary. Variable length subnet mask works the same way, but we do one grouping at a time. Used to create subnets containing a different number of hosts, and applies a host subnet mask to the IP address and provides the number of hosts required. The increment required to do these things is first divided into subnets, and then some of the subnets are divided into subnets, so we're subnetting subnets. And some of these are further divided. Detailed structure of this. Let me try to do, and actually let's see if I can write on this one. I may need to, it's usually easier, let me get paint started here, or try to, and make it bigger. All I want is a big area that we can write on. So in this one we have subnet 1, we have 5 hosts, so we got 28, 12, and 5. Let's say that we want 28 and 12 and 5 hosts, and it really doesn't matter which we have here. So our hosts, we had 28, 12, and 5. Let's make that a little bit bigger. What we do with this thing, and let's say that the network that we want to affect 192.168.1.0, and that's 5.255.255.255.0. What we're basically going to do is start filling up the bucket. So we're always going to start with the largest number. So we do that 2, 4, 8, 16, 32 hosts is what we would need. So our network address, the first one would be 192.168.1.0, and we needed 2 to the n, which would be 5 bits for hosts. And if we do our 256 minus 32, we're going to get a 224. So the 192.168.1.0 with a 255.255.255.224. Now in this case we've used 32 addresses, so our increment would be 32. The next network address would be 32 here. I'm not going to write that whole thing down, 1.32. We go to the next highest number, which is going to be 12, will be 2, 4, 8, 16, which is 4 bits. So 16, 32, the next address would be 48. We're going to get to these in a minute. .1.48, right? Because we used 16 addresses in here, 16 total addresses. Our subnet mask, 256 minus 16, 0, 240. So our subnet mask would be 255.255.255.240 in this one. So, and then the next network address for the 5 hosts, and we don't have to we can keep going here, but a 248, which would be 8. So our subnet mask would be 248. We could then keep going, but at this point 248, and see what we had, we said 248, we did this, so 56 would be the next available network address that we could do. So we have now created networks that have different number of hosts in them, called variable length subnet mask. And again, there's a video goes through the same process that will be part of this. Same process applies. A custom subnet mask network is divided, and then we did the dividing the divider. And this is the example here. We talks about 28 hosts, 5 bits, 32 would be the increment that we have. The subnet is 192.168.1.0. The mask 256 minus 32, which gives us the 255.255.255.224. The broadcast would be 192.168.2.31. The next network address minus 1. The next network starts with 32, since we used 0 through 31 in our prior network. 12 hosts, the 16 increment, 240 for the subnet mask. The network address would be .32. Our next network would be 32 plus 16, 48, because we use 16 addresses in this subnet. The broadcast would again be the next network minus 1, in this case would be 47, and then the 5 hosts, the increment would be 8, the mask would be 248. So a way to do those quickly with the increment. Review, we're going to subnet for a lot of reasons: efficiency, security. We're going to create a lot less broadcast traffic when we do that. Security, because we don't see the broadcast, we don't see the other systems are separated by that router. And the subnet mask we talked about, the subnet mask tells us how much of the network, or how much of the address is network and how much of the address is host. We looked at the subnetting process, CIDR, which was everything was the same size subnet, and then the VLSM, the variable length subnet mask. The next topic is going to be quite a bit shorter, so we're going to talk about the unicast, broadcast, and multicast, which will take just a couple minutes, to a few minutes, 5 minutes or so, fewer minutes than this one took to do. So hope to see you there.